So first, thank the organizers, and in this sense, Ethan, for inviting me to give a talk. And second, thank you, Ethan, for saying half of what I wanted to say in your impromptu talk Monday. And of course, Stefan said the other half of what I wanted to say already. So I will say the third half of what I wanted to say. So Ethan asked me to talk about two-photon exchange at MUSE. And I will give some history of two-photon exchange and my involvement in it. This will be about 2/3 of my talk. Some of you have been in this field for a long time and know about two-photon exchange as developed to be important in Jefferson Lab, and my apologies if I'm telling a story you already know. And then we'll talk a little bit about two-photon exchange in MUSE and conclusions. Okay, so first, this is just a personal background. I grew up not doing electromagnetic scattering, but doing pion scattering, and then I moved to electromagnetic scattering as a postdoc. And the first thing I learned about radiative corrections is they weren't important. They were small and well understood, and I didn't have to worry about them. So I didn't need to learn anything about them. That didn't last too long. Okay, and when I went to Rutgers, I ended up building the polarimeter for Hall A in Jefferson Lab to do proton recoil polarimetry. And the important point for the purpose of this meeting is the set of GEP experiments at Jefferson Lab. The main GEP program, of course, was led by Charles Pedrosa, who won the Bonner Prize for it because of the surprising results. So the initial GEP goals, when we started out running our first experiment back about 1998, and I believe Stefan and I are the only people here who were collaborators on that experiment. The initial goals were to study the proton structure at high Q-squared, because as we built Jefferson Lab, the idea was to see about effects of quarks in nuclear physics and structure of hadrons. So we actually knew already the answer we were going to get in the experiment. And the answer was that GE and GM both roughly follow the dipole and look like each other in their Q-squared dependence. So we were just going to do an experiment that improved our knowledge of that. So we wanted to determine GE, we wanted to determine Q-squared F2 over F1. We wanted to look to see if there was an approach to perturbative QCD, because when we started doing this, there was some belief that we would see approaches to perturbative QCD, which also turned out to be wrong. Okay, I'm neglecting here the Bates and Mainz polarimetry efforts. And just for a little bit of completeness, when I say I built the polarimeter, there was a collaboration that built the polarimeter, and it was based sort of half at Rutgers and half at William and Mary, Norfolk State, Regina, and Jefferson Lab. Okay, so let me turn to GEP more explicitly now. So the electron scattering cross-section, I've made an effort in this talk to have no formulas. So all my equations are in 2 appendix slides after the conclusions, and I will present no equations during the body of this talk, I believe. My apologies to the theorists. The electron scattering cross-section depends mainly on the magnetic form factor at high Q-squared, mainly on the electric form factor at low Q-squared. That makes precise extractions of the small component difficult. This was recognized long ago. The Rosenblum separation dates to the late 1950s, and already in the late 1950s, people understood it was hard to get the small component, and you had to do something different. And already in the late 1950s, early 1960s, theorists explained to us that by using polarization, you could get quantities that were linear in the small component and do a better job of extracting them. And it only took experimenters about 40 years to catch up. So this was the best result before we started running at JLab for the electric form factor at high Q-squared. This is the results of Lisa Andivahis and collaborators from the NPAS program at SLAC in the early 1990s. I've pulled figure 22 out of the article. These are the Rosenblum separations, and I assume in this audience, I don't have to define Rosenblum separations. The reduced cross-section versus the virtual photon polarization epsilon. The intercept is tau GM. The slope is GE. As Q-squared increases, the slope goes down generally a little bit, with an exception here. When you extract GE from these data, you get the pattern shown over here. The Andivahis data are the solid points, and they sit at mu GE over GM is very close to 1. Okay, so returning to the doing better with polarizations, most of the experimenters seem to have forgotten the theoretical work of the late 1950s, early 1960s. It got repopularized among us as we were heading towards Jefferson Lab by the 1981, the early 1980 articles actually of Arnold, Carlson, and Gross, who took the formulas from earlier work and put in form factors and gave us estimated polarizations, both for protons, for neutrons, and for deuterons. So the earlier work was by Dombey, by Schofield, and by Achiezer and Ricallo. And if I can remember correctly, after all this time, when I went back to the Dombey and Schofield articles, they were in a different notation and I didn't understand them. The Achiezer and Ricallo articles were the first ones using modern notation, the same as used by Arnold, Carlson, and Gross, and the same as used in the talks you've seen today, or earlier by, for instance, Ethan. Okay, so we ran GEP1 in 1998. We put in a proposal a few years earlier. We already knew the answer, of course, and the PAC already knew the answer, so it was not considered an important experiment. It was given B+ priority. When we measured, instead of finding that the form factor ratio was 1, we found that it decreased almost linearly with Q squared. This led to a lot of work, and we've often since referred to it as the most highly cited correct result from Jefferson Lab. I believe there's still one more highly cited result that is not correct from Jefferson Lab. Yes, I did hear pentaquark in the background, and that is indeed what I was thinking of. The early 2000s pentaquark as opposed to the recent pentaquark. Okay, so this contradicted the earlier results. And as experimenters, what we initially focused on is, of course, what did the other group do wrong? So those of us involved in the polarization program were wondering what the cross-section people did wrong. And those who were involved in the cross-section program were trying to figure out what we did wrong with our polarimetry. I know that several people I worked with doing other experiments were telling me that as soon as we got some more polarization experiments with different techniques, we would see that we were wrong in our recoil polarimetry. Okay, so the first follow-up we actually did was from Olivier Gaillou, Krishna Vijayasuriya, and all. The polarimeter was used for several experiments, and when you use it for EP scattering, there's actually two things you determine when you do the polarimetry, and one is what you actually measure in the polarimetry is an azimuthal distribution and azimuthal asymmetry in the proton scattering from the polarimeter, and the size of the azimuthal distribution measures the polarimeter analyzing power, which is useful for other experiments. And the phase shift in the asymmetry measures the recoil polarization of the proton direction, which is related to the ratio of electric to magnetic form factors. So we regularly did EP scattering to calibrate the polarimeter for other experiments. And one of those sets of calibrations we published in Gaillou and Vijayasuriya. And let's see, this is the longitudinal component extracted from that. And the longitudinal component depends essentially on kinematics and not on form factor ratio. And the transverse component depends essentially linearly on the form factor ratio. And you can see these data tend to fall towards the solid line, which is the form factor ratio being reduced below 1, as opposed to the dashed line, which is the form factor ratio staying at 1. And then the next year, we published an article by Olivier Gaillou, which is the oh, I'm sorry. This is the G over GM values from the Gaillou Vijayasuriya article. Okay, so the next year we published the extended higher Q squared measurements by Olivier Gaillou using an improvement of the polarimeter, and that's these points here. And we continue to see the linear fall off of the form factor ratio with Q squared. And here I present one of those azimuthal scattering distributions from the polarimeter. And basically we're measuring the phase shift here, and that determines the ratio of polarization components, and that determines the ratio of form factors. And the difference between the dashed line and the solid line that fits the data is the difference between the form factor ratio being 1 and falling off. Okay, I'm going to skip just a little bit forward in time and ignore some things for the moment and bring back the super Rosenbluth measurement. We were confident in our polarization measurements. There was a question of, what had done wrong experimentally. John Arrington proposed doing super Rosenbluth. The super Rosenbluth results came out and confirmed at the level we trust the super Rosenbluth, confirmed that the form factor ratio with cross sections is around 1, and with polarizations decreases. And I'll skip even more forward in time. When we did the polarization experiments, we believed that we didn't have to worry about radiative corrections in them at all. And let's see, to first and maybe second order, I will assert that we don't have to worry about radiative corrections in these sort of polarization experiments at all. The one thing we do have to worry about when we go to high Q squared is within our acceptance, there's some inelastic contributions. And you do have to be careful to separate out the inelastic contributions and not integrate over them. But particularly at low Q squared, we do most of these experiments with coincident detection of electrons and protons. We believe the measurements are clean, and we integrate it over the elastic peak to determine our data. So fast forwarding the few years towards 2010, we got interested in measuring at low Q squared. And we measured a series of data points at low Q squared. That were the John et al. Data points. So first in 2006, the Guy Ron et al. Data points, which are shown as the open triangles here. And second, a couple of years later, in 2008, I think we actually did the measurement of the John et al. Points, which are the solid red points there. We wanted to map out the ratio very precisely at low Q squared because we realized the ratio of form factors at low Q squared was also, of course, a mess, and we should determine it better. When we did this, to do it well, we decided to take about 10 times as much data as we ever had before. And when we took 10 times as much data, we found we could cut out how far out on the elastic peak we went. And then we did find out that if you go enough into the tail, you do change the polarizations you measure and the apparent form factor ratio. So we did find we needed to be a little more careful than we had to believe. But we still believe that if you cut enough on the elastic peak, then we can totally ignore radiative corrections. And this is why polarization measurements are better than cross-section measurements. Okay, so there were small percent level effects if we integrated over our entire acceptance. One of the things I wanted to point out here is that in the polarization data, the data look kind of ratty here still if you compare our data to older data. A big set of the data here, the diamond points are from the Crawford et al. Bates experiment, which is a polarized beam, polarized target experiment. And I think Michael actually was part of that. We've always believed on the Jefferson Lab recoil polarimetry side that one has to be real careful about knowing the angle of the polarization of the polarized target. And we always worry about how well that was known in the Crawford experiment. There's clearly an offset between Crawford and between what we measured.
Yeah, I mean, you have the spin transfer and
yep.
the precision problem. And in class, we have the target orientation, which varied along the extension of the target. And we had to use some clever compass needle technique to map that out. And that was one of the largest systematics.
So we
and not taking into account, obviously, if this explains the difference.
No, the systematics are included in the data.
But then there is a discrepancy.
Yes.
Yeah, of course, this is another case of experimenters each believing the other.
So what was never really established up until then is whether the two polarization methods are really giving the same results and if they are fully equivalent.
Theoretically, of course, the answer is yes.
Yeah, and there was another experiment then at somewhat higher Q squared up to 1 point or 2 GeV squared using polarized ammonia target.
There was another experiment at Jefferson Lab I have not talked about that in SANE there was, yes. I believe. There was
I'm referring to that, yeah. And that showed a decline and was also consistent with the recoil polarimetry.
And I should also mention, just for completeness here, that the flow measurement actually got Stephan's measurement, and that's part of a helium-4 experiment, also done very precisely and independent of these. This has always troubled me a little bit, and in part it's troubled me because I very much trust our data because we did a lot of systematics with COSY, and we could look at things like what result you got from different parts of the spectrometer acceptance and whether the spin transport made sense. And spin transport is fairly simple, and the spectrometer is very well mapped. But it troubles me that there's a disagreement, though I very much trust our data, but it also troubles me that every time I look at our data, it looks fairly linear in this region. And if reality really was fairly linear in this region, that means you're getting something a little funny happening in this region compared to theories. So it's always been a little concern for me. Yeah, please, Michael.
the lowest Punjabi point troubled me the most on this plot.
One of the, I will say, one of the issues as we learned things as we went on, when Andrew Puckett did the very highest Q-squared measurements that I haven't shown and saw the effects of the inelastic backgrounds, that caused the Guyot measurements to be reanalyzed. But the Mark Jones Punjabi GEP1 data was never reanalyzed carefully. So I always worry about that a little bit. And yeah, I'm concerned.
But that was the same setup and technique, but just different people utilizing it.
Well, it was largely, it was the same collaboration evolving with time. Mm. Sorry. Well, there was a calorimeter in the first part,
and there was a calorimeter for the first GEP experiments. Or
GEP1 was running poly-HRS, GEP2 was running poly-HRS with an upgraded polarimeter, GEP3 was running Pol-C with a new polarimeter.
Yeah, so the apparatus changed.
Yeah, but Punjabi points that Michael's referring to were running the same spectrometer as John and all. So in this plot here, all the recoil polarization was running the same spectrometer by the same group of us evolving over 10 years in time. And the exception here is the profit points, which were the Bates glass polarized beam polarized target asymmetries. So I think that John data and the Photon point were all run very high statistics and our best set of data. They were the last ones run as we learn more things and we're more careful about backgrounds.
You do have an equation on this slide.
I do have an equation. Oh, Q squared equals 0. Yeah. My apologies.
Also, when you say we believe that 3D interactions were small, we actually did calculations as association very close. That was 2001 paper where we actually exactly calculated the correction within your cuts. Calculated corrections within your experimental cuts, standard QED correction, and it was 10 to the minus 4 level, something like that.
Are you willing to agree that 10 to the minus 4 is 0 in this context?
We just did.
Okay.
If you integrate over defined threshold, up to the defined threshold, only so.
Yeah, and we of course don't go anywhere near pi on threshold in these measurements in coincidence.
Yeah,
at low Q squared.
Yeah. That said, oh, if you have only, there was a paper by Maximon published seriously that he said, oh, if there is soft photons only emitted, you don't have any corrections. That was actually published. We knew that, but we included hard photons, and that hard photons can slightly change your polarization observable, but at a very small level.
Here's what I will say, Andre. In the normal cross-section experiment, you measure a few percent cross-section with a 20% radiative correction. And in the polarization experiment, you measure a few percent polarization with an effectively 0 radiative correction.
Yep.
So we should all do polarizations all the time and make life difficult for theories. Okay, I go back in time now, and I can't comprehensively review everything, but I put in a bunch of references, some hopefully large enough set of references. Back in 2003, was about when we started hearing about two-photon exchange, late 2002, 2003, and we started hearing that this was the solution to why the cross-sections and polarizations were different. And London, Melnichuk, and Sean article in PRL, followed up by an article in PRC, Sean Vanderhagen, I mentioned PRL, Bacallo and Egley, I mentioned the EPJA article, Andre and collaborators in PRL and in PRD, and I just quickly point out that in PRL, the author list was in one order, and in PRD, the author list was in another order. And in the next few slides, I'm going to show some calculations, and I will refer to them with things like BMT, GB, AB, CCV, or something like that. It was alphabetical, I believe, in the second article.
Alphabetical in the flat preprint for the first paper. And then when Mark submitted the paper to their letters to change the order.
Okay, so here, this is BMT. This is the Rosenblum separation data. This is with two photon exchange correction. This is the polarization data. They come closer together. Here's GV. This is the Rosenblum. This is the polarization. There's the correction brings it over corrects here. And this is Andre's article. These are the Rosenblum data. This is the corrected Rosenblum data with two photon. These are the polarization data. We certainly all started believing it was very plausible the two photon exchange explained the difference, even if we weren't getting exact agreement, and even if we were doing this in very different approaches. So somehow all the approaches were showing things got better. Okay, that led to a large program starting in the early 2003 of proposed experiments at Jefferson Lab to try to really constrain the two photon. And there are various things that were considered, looking at Rosenblum separations for nonlinearity from the two photon, looking at angle dependence to PT, or generally the polarization observables, non-zero normal polarizations, PN or AN, not easily done at Jefferson Lab, positron, electron cross-section ratios. So I have a sample of data here. I did not include the beam normal asymmetries from the parity violation experiments, and I didn't include the target normal asymmetry from helium-3, but I did include a bunch of other results. So this is, again, these two figures again are from Andre, and this figure here is showing the expected curvature in the Rosenblum separation data from Andy Vahis. And you can see that the curvature is small, much smaller than the experimental errors. And it would be very hard to detect even with errors a few times better. This is the polarization transfer, and you can see it depends on kinematics, and it has some curvature. Normally, we only did these points at a single epsilon value, but we did do an experiment as a function of epsilon, which I'll show in a moment. Then there were normal polarizations. We had interest in normal polarizations, but there's a problem. This is Andre's calculation, and this is Peter's calculation. And the problem is the calculations show us that the normal polarizations are all of order 1%, and getting false asymmetries in polarimetry down at the 1% level turns out to be hard. So it was just a little bit too hard for us to do. Okay, this shows Andre's calculation for the positron electron cross-section ratio. This is some set of old data here. This is the calculation, shows the ratio goes negative and then positive, and the data has large uncertainties. In fact, the person who tried to data mine all the old electron-positron data and make sense of it the most was John Arrington. And these are two figures from John Arrington's article, the electron-positron ratio versus Q squared, which shows at the level of the data, the ratio is 1 and generally has a few % uncertainties. And if you look instead at versus Q squared versus epsilon, now we start to see a pattern where at high epsilon, the ratio is close to 1. And as you go to lower epsilon, the ratio gets big. But again, with big uncertainties from the old data, not that convincing. Okay, we decided to look at the polarization transfer as a function of epsilon. This was an experiment led by Lubomir Penchev, appearing as Messiani et al. In Physics Review Letters. This is the epsilon dependence. Here's the form factor ratio. We took 3 points, 1, 2, 3. You can see it goes down to epsilon of about 0.2, where we would have liked to see some curvature based on Andre's calculations, up to about 0.8. And what you see here is we don't see any epsilon dependence in the polarization transfer ratio. But when you look at the longitudinal polarization only, for some reason, this point's about 2% higher than the others. And that doesn't look like what any of the calculations estimated, so I don't know what to make of it. Again, the individual polarization component depends on knowing the analyzing power. So essentially those data are normalized to the last point, the lowest epsilon point. So I don't know whether that's significant or not. Okay, then we had all the E plus, E minus experiments. There was the Novosibirsk experiment, the Hall B class experiment, which Andre was a spokesperson of, right? Yep. If that's allowed. And the Olympus experiment. And in the end, the best result is the Olympus experiment. And here again is the Olympus data you've seen before, maybe hundreds of times from the published Olympus article. And Peter's calculations and Jan and Tomalak, two-photon exchange, and the other figure from the article, the difference with Peter's calculations. And I think a lot has been spoken about this, and all I think I want to say is my view is that the two-photon exchange data here and the theory are about the same size of the effect, but if you pick the wrong theory curve, you can have the opposite sign. And that means if you're using two-photon exchange theory for corrections, you have to wonder what the uncertainty is on the theory correction you're applying. And I'm sure we have a variety of theoretical opinions on what the errors are on different theoretical curves. So all I can say is I'd say it looks like you can be 100% or 200% off on the theory correction if you're not careful. I think I'll leave it at that. Okay, as a personal note now, this is again an aside. Here's the John et al. Data, and Guy and I and Ellie and others led that experiment. When we were doing that experiment, we didn't have an intent to extract a proton radius, but before we finished the analysis, the muonic hydrogen result came out. So that meant we took this data and the world data, other than Jan's data, and fit the world data and extracted a radius. And that meant we got this radius here that was entirely consistent with the other old electron scattering analyses. And in 2011, in a nice meeting in Marrakesh, Michael and I were talking over a coffee break. And we said, what are we going to do about this muonic hydrogen? And we said, why don't we scatter muons? And that's led to a decade of effort in Switzerland. Okay, so I think Stefan already showed this exact figure. So the idea was we use electron and muon scattering at the same time in the same apparatus to compare cross sections. Form factors and proton radii would reduce systematics. I have a star here because I just want to note, although this hasn't come up, and I will not actually show this formula, that there are mass terms in the cross section that are ignored in almost every electron scattering article, and these change the cross section by numbers like a factor of 2 or so, depending on your kinematics. And if you want to see the mass terms, they're nicely published in the same form as the usual Rosenthal separation. So I give the reference. And other than saying that, I'll ignore it. Okay, so this was one part. The second part, beams of both polarities for two-photon exchange measurement. That ties into today's topic. As Stefan mentioned, check of conventional initial state radiative corrections. And I also mentioned our beam ranges from, at low momentum and negative polarity, our beam is 97% electrons. At high momentum and positive polarity, our beam is 90% pions, and the amount of electrons and muons and pions varies. So we also get these pion backgrounds that are of interest to people doing pi p phase shifts. But other than that, I will not mention pions. Okay, Stefan already told us our beam momenta 115, 160, 210 seem to be the standard momenta we run at. These are not the momenta in the initial proposal, which I think are 117, 153, and 210. The angle range is about 20 to 100 degrees. The Q-squared range is about 2 times 10 to the minus 3 to 0.08. It varies a few percent between electrons and muons because of the mass. The epsilon range is 0.94 to 0.27. And I tell you that because remember that in most of the data we've seen at epsilon around 0.97, the two-photon is close to no effect in it. 0.27, the two-photon is a large effect. And yeah, the kinematics are slightly different for electrons and muons. Okay, so Olympus comparison suggests two-photon exchange corrections about the right size, but maybe opposite in sign from a particular estimate. It seems to be typically of order of percent, with the slope near epsilon equals 1. So it has the potential to significantly affect a radius extraction if you don't do it or do the wrong 2-photon correction. And if you can measure the correction, you should, and we can measure it, so we should. We recently got an article with calculations about the sensitivity in arc kinematics to the radius in dispersively improved chiral effective field theory, which you might be familiar with. There have been a bunch of articles by Christian Weiss and collaborators on this in the past few years. So we have a preprint from them, which I believe has not appeared on the preprint server yet, but Christian told me I could show some figures and mention some results from their calculation. The basic result is that nearly a percent change in cross-section results from 0.01 Fermi. Sorry, if if the radius were different by 0.01 Fermi, it would change the cross-section by nearly 1%. And the 2-photon is nearly 1%. So you can easily get 0.01, 0.02 Fermi errors in the radius extraction if you don't have the right 2-photon. Okay, so it's potentially significant. I want to quote from their article here. Just this is my limit of my theory discussion. The cross-section is computed using equation 42 of reference 6. Reference 6, Tomalak and Vanderhagen. The 2-photon exchange corrections are added according to equation 44. Their values extracted from figure 14 of the same article. Thank you, Alexander, for doing all the work. I have 2 sets of figures from the article. This is one taken at 153 MeV, where we're not quite running, and this compares the 1-photon exchange to the 2-photon exchange. And you can see it makes a difference of 0.5% here in the middle of our kinematics, and nearly 1% here in the middle of our kinematics. Note that this is electron-proton scattering, and this is muon-proton scattering. And then I have another figure for their article. This is the expected variation of cross-section with Q squared at 210 MeV for a bunch of different radii, 0.83, 0.84, 0.842, 0.85, 0.86, 0.87. So this is roughly the range of the radius puzzle, 0.84 to 0.88, or 0.84 to 0.87. And that's roughly a 3% effect. And 2-photon exchange is roughly a 1% effect. And you see roughly the same thing whether you look at electrons or muons. So I just repeat again, 2-photon exchange is kind of a 0.01 Fermi correction or 0.02 Fermi correction is important to get right. Okay, these are the projected data. Stefan has shown them. This is from mu plus to mu minus, and the error bars grow. We of course get electromagnetic scattering, so we get decreasing counts as we go out an angle. And the error bars go from sub 1% to a couple percent. The electron statistics, the number of counts we get for electrons range from a couple times more to up to about 30 times more, depending on kinematics. And so I say here the statistics are 2 or 3 times better, but they're at least that. The systematics are estimated to end up at 0.2% when we do the differences. Okay, so that's my story. What are my conclusions? 2-photon exchange is important for precise experiments. The level of agreement between theory and data is not yet sufficient for precise experiments. It could be that there's some interesting theory to learn. It could be that we just learn about experimental issues in the end. And of course, I don't know where we'll end up there. And corrections are significant for precise proton radius, and MUSE will measure what we need. Thank you.